Good evening, everyone. I think we have waited long enough for those who are yet to join. Please give me a thumbs up if you can hear me clearly, and then we start the meeting at once. Okay. And I believe you can see my screen clearly too, right? So today's lesson will be covering chapter 5 of the Stallings Manual. Before we do that, let's recap what we were learning the last time we met. So last time we were discussing chapter 4.1, but chapter 4, actually. We were almost done with it. However, we were not able to cover it fully. There was one more lesson to cover. I think we were stuck a little on working on it. What do we call it? Average memory access time, the recap. So it took us quite a while and then we abandoned the lesson. From there on, it has been assignments and assignments. So it's not hard time to go back to it. But let's just recap it quickly. So we learned about average memory access time, and then it's just basically talked about how long data or CPU takes to get data from its individual memory storage spaces. So how cache is able to give, so during one processing cycle, how fast or how long it takes cache memory to retrieve data and give it to CPU for processing, and etc. etc. To calculate all these things, we need to consider how many different memory spaces are involved in a particular processing cycle. And after we determine that, we can compute the average memory access time. And then we saw the formula to be the average memory access time is the hit time in the L1 cache. So the amount of time it takes the level 1 cache to identify data that is on it, plus 1 minus the miss rate. So 1 minus the miss rate means 1 minus the probability of it finding data that is not inside level 1 cache. And then finally it says times penalty. Penalty is the access time for RAM. In other words, how long it takes RAM to allow data to move from it to a higher level memory. That becomes the penalty. So to compute it, we take hit time and we combine it with the products of the miss rate and the miss penalty. Some examples are given as this. So it says, let's say you've been given the parameters, level 1 hit time is 1 nanoseconds, meaning that it takes 1 nanoseconds for the cache, level 1 cache to find data that has been stored on it. And then it says that the level 1 miss rate means the probability of not finding data on the level 1 storage and having to go outside it to retrieve data is 5%, which is equivalent to 0.05. And the miss penalty, that's the access time of RAM, or how long it takes RAM to let go of data for a higher level memory to access, is 100 nanoseconds. So then to compute it, we take hit time, which is 1 nanoseconds, plus the product of miss rates, which is 0.05, and then the penalty, which is 100 nanoseconds. So 0.05 times 100 nanoseconds, as you can see here, gives us 5 nanoseconds. And then you combine that with the hit time, and that gives you exactly 6 nanoseconds. This is what this value here, the 6 nanoseconds, becomes the average memory access time. We're also aware of the fact that it differs from RAM, the type of architecture or storage architecture we are using. We learned that if it is inclusive, where data for a higher level can be stored at a lower level, you will have to compute and then take into consideration level 1 and level 2's access time too. However, if it is exclusive, then you would either have to calculate for level 1 or level 2, irrespective of the other. So there's a question here from that. It says if a cache has a hit time of 2 nanoseconds and a miss penalty of 200 nanoseconds, what must the miss rate be to achieve an overall average memory access time of 4 nanoseconds? And we know the formula for average memory access time. So since we are recapping, we might as well do the working for this one right now. So let me. Okay. It looks like I'll have to go outside this to do that. I don't want to leave this file just to go do that. Anyway, we can use our minds to compute it. So we know that the formula says the average memory access time, which is AMAT, is equal to the hit time plus the product of the miss penalty and the miss rate. So we have to calculate the miss rate. So we just have to do some change of subject. So for average memory access time, which is 4, is equal to 2 plus 200 times the miss rate. So let's say that is x. So 2 plus 200x and is equal to 4. So if we group like terms, we are going to have 4 minus 2 is equal to 200 nanoseconds. 4 minus 2 gives us 2, and 2 is equal to 200 nanoseconds. It means we just have to divide both sides by 200 to get x standing alone. That will become 2 over 200, which is equivalent to 1 over 100. And that gives us 1%. So 1% is the correct answer for this particular problem. All right. And then yes, so for the memory hierarchy, I believe we are familiar with them. We talked about it the last time. We mentioned the order in which the hierarchy changes. Which one has greatest speed, which one has greatest size. We mentioned that there's a trade-off when it comes to these things. Starting at the CPU, we have the level 1 cache. Level 1 cache is the fastest memory there is. However, its size is very small and it's also very expensive to produce. And then we have the level 2 cache, which is slower than level 1 cache, but it has larger space. So it means there's a trade-off between space and speed. So the access time of a particular memory is reduced if its size is increased. And then there is the main memory that has the large capacity as compared largest capacity of them all, not all memories, but in terms of cache, the main memory has the largest. And then the main memory has the largest capacity, but that will mean that it has the greatest latency too. It takes the longest time to for data to be accessed from it. All right. Then we also looked at the policy implications. There were the inclusive and the exclusive. We talked about inclusive, where we said a lower address holds a higher address's data, just so that it can be easily retrieved when needed. So inclusive stated here says level 2 holds level 1 data. Exclusive says level 2 avoids level 1 data. This one allows for the maximum use of the capacity, storage capacity, but it complicates eviction because it makes it hard to get data. If you want data from level 2 and you cannot access level 2, this means you will have to go to the RAM to get that data, thereby making it harder to run something that would have been simple if level 2 held it. So if level 2 in inclusive plans, if level 2 holds level 1 data, what this means is that there will be less space or less bandwidth in level 2. However, it will still allow you to easily get data that you need. At least for most of the data you need, you won't have to go to RAM. So that's what the inclusive and exclusive mean, and that's where they differ. Then we looked at some other calculations. This one is on an inclusive policy model where level 2 stores level 1 data as well. So let's see how that works. It says in the question, we have been given the RAM access time to be 100 nanoseconds, and then the hit time, it means the chance that's if you successfully get data from level 2, the time that it will take you to get that data out of level 2 is 5 nanoseconds, and level 1 hit time is 1 nanosecond. So it takes only 1 nanosecond to find data that is already on level 1. In order to compute in a question like this, what we actually do first is we find the access time for level 2. Since level 2 will also be picking data from RAM, we find the access time from level 2. And then when we compute that, we'll use that as a penalty when we are computing level 1 score. So in order to compute level 1, you have to first compute level 2. That's basically the idea. And that is for inclusive. So what's happening here currently is it takes the level 2 hit time, which is 5 nanoseconds, plus the miss penalty, which is the product of the miss rate for level 2, and then the penalty for the RAM. So if you come to this side, the system spec, the parameters have been given. It mentions that the level 2 hit time is 5 nanoseconds, as you can see here. And then the rate is 30%, that's 0.3 here. And then the memory penalty, that's for going to RAM, is 100 nanoseconds. So if we multiply that, we get 0.3 times 100, that gives us 30. And combine that with 5 nanoseconds, and then you get level 2 access time to be 35 nanoseconds. So if that is for level 2, now we have to calculate level 1 because we want average memory access time. It means all in total, roughly how much time do we spend per cycle of access. So after doing that, we go to level 1. And now when we go to level 1, the hits time for level 1 is 1 nanoseconds. It means if the data is already on level 1, then it only takes us 1 nanoseconds to retrieve it. But if it's not there, what's the probability of it not being there? According to the question, it says the miss rate for level 1 is 10%. It's a hand up. Okay.
Okay.
So, yeah, okay. So according to what it says here, it says that level 1, the probability of you not getting data from level 1 is 10%. This means if that 10% succeeds, we'll have to visit level 2. So we have to take that probability into account. So we take the chance of we not getting the data from level 1, that's 10%, and we multiply it by the speed at which level 2 allows us to take data. Remember that speed, originally it was supposed to be 5 nanoseconds. However, due to the fact that level 2 is now dependent on RAM as well, RAM's values have influenced level 2, changing the access time or the hit time from 5 nanoseconds to 35 nanoseconds. This means this time it takes into account RAM's and its own hit time too. Therefore, the level 1 miss rates is 0.1. And then the access time for level 2 now becomes the penalty, because that will be how much time it will take us to retrieve data from level 2. So that's 0.1 times 35. And then if you compute the two values, this finally gives you, I think this gives you 3.5, and you add that to 1 nanosecond, you get 4.5 nanoseconds. So yeah, that's for a multi-level problem, right? So there's a question that we were asked. It says in an exclusive cache hierarchy, the total storage capacity of level 1 and level 2 combined is strictly greater than in an inclusive hierarchy. Please, Ewa says he can't hear me. Is that that's everyone? Is that true for everyone, or is just him?
It's
For
only
my,
him. For my end, it's
it's
working.
just him. Okay. So, Mr. Ewa, please, if someone can't, please tell him in the chat to exit and join again. Let's proceed. So then the question here, we answer, we've already done this one. So we are just recapping because it's been a while. So in an exclusive cache hierarchy, the total storage capacity of level 1 and level 2 combined is strictly greater than in an inclusive hierarchy. Assuming the same physical hardware sizes, is this true or false? Remember that in exclusive, data for level 2 is stored in level 2 only. Data for level 1 is stored in level 1 only. The only place you can get extra data from is from the RAM. So then they are asking you that if I combine an inclusive system, the capacity of storage there for level 1 and level 2 together, is it greater than what is in an inclusive? In an inclusive, we have data for level 1 being stored in level 2, as well as level 2 data also being held in level 2, leading to doubling of data. You say that exclusive has greater memory capacity in total than inclusive? If you know the answer, the floor is open. Okay, so then the correct answer to this one is that it is true. So exclusive does have a greater storage capacity, seeing as it doesn't bother with holding data values from level 1. This means it freely makes use of its space. So it's true. All right. We have already looked at some of these concepts. This one, transfer rate versus cycle time. The cycle time is how fast the request starts, and it's only limited by the memory physics or refresh rate. Transfer rate, on the other hand, is how many bits are moved per second, and then it is limited by bandwidth or frequency. The bandwidth talks about how narrow or how wide the chamber through which data will travel is. If it is very narrow, then it means data will move at slower speeds because it is confined to a smaller area. However, if it is wider, then it moves faster. So it says a high transfer rate is useless with high latency. High latency means that it takes a lot of time for that particular memory to access data, or memory access time on that side is very high. So it means it's latent. It takes a lot of time to give out data. Low latency is wasted on low bandwidth. So if memory is able to give out data very fast, so if cache is able to give out data very fast, but the channel that is transferring the data is still very narrow, then it means that the speed of the data being provided will become a waste now. So it becomes useless. So reducing latency for lookups and increasing bandwidth for bulk exports. This is how most administrative databases work. They do this. So when we are just searching something, right? If you are just searching something, it reduces latency, just that. And it increases bandwidth for when you are doing a lot of movements of data. So when you're moving a lot of data, it broadens channels. So it allows for data to flow through wider channels so that the movements can be faster. All right. So these are all questions on that. So I think that's enough for the recap. Let's look at the next one. The next lesson we're supposed to look at the last time we met. So be covered in further detail in the lesson to come right now. So I believe we can actually leave it here and go observe it in the lesson that we are coming to tackle. But let's breeze through it first. So advanced cache design. So by the end of the lesson, you should be able to examine sophisticated cache mapping and replacement policies like least recently used, LRU, or you can apply analogies to understand how it works. Let's get right into it. So now let's start with the replacement policy. Now, due to the fact that we've already established that cache is actually very small in size, this means that it cannot hold a lot of data at a time. But we are aware of the fact that the CPU uses data, and then due to locality policies, it's sometimes when it is fetching data, it fetches data that are likely to be accessed to. But if cache is so small, when these data are fetched, where exactly are they going to be held? To be held, sorry. This means that data must constantly be removed and replaced by new data in these memory spaces. The rules that embody or the type of replacement that happens is what we call the replacement policies. So it says there is a cache eviction policy, and it decides which block to replace when new data is being added. So cache eviction policy decides which block to replace when new data is being added. Then we have write buffer. That's a small temporary storage area holding data for the main memory, letting the CPU continue working. A small temporary storage area holding data for main memory, letting the CPU continue working. So then this is like a temporary storage. This is just a temporary storage unit that you use to hold data. It will be able to hold data from main memory. This means it has more space than your average cache, but then it still makes it possible for data to be easily retrieved. You understand? Makes it possible for data to be easily retrieved. And there is the cache mapping. The cache mapping talks about how we move data from a particular memory block into a particular cache space, and we'll be looking at that further in the lesson to come. So mapping around to cache. And then there is inclusive hierarchy, which is inclusive, that's level 2 holds all data from level 1, a copy of it to be precise. So this will be covered in the next lesson, even better, and we are going to do that. So let's look at it on the surface. There is the direct mapping. In direct mapping, what happens is when we go to a particular memory address, each single memory address is assigned a strict path in cache where its data is supposed to be held. So it means each memory address is assigned to one particular cache storage space. What this means is B4 here is currently mapped to L0, and it can only go to L0, and it cannot go to all these ones even if L0 is empty. There are advantages to this. The advantage is that it makes it simpler to identify where exactly data should be held, since every data is assigned a particular cache. to move from memory into. However, there is a trade-off. Since every data here, and you can see memory has more capacity than cache does. Every data is assigned one space. If two data with around the same popularity to the CPU, if each one has about the same priority in CPU, are supposed to be held inside a particular level, like level 0 right now, what will happen is both data will constantly be at conflict, fighting for who stays and then who goes. The CPU will be struggling to decide who stays and then who goes. So to make the right decision. So then the advantage is it makes it faster, or it makes it easier to identify the spot where we are going to hold. However, this speed is quickly taken away by the fact that if new data and old data are both held in the same space and they have similar priority, there will be a conflict between the data as to which one should be held and which one should be let go of. So that's the direct mapping. Each memory address is assigned to one particular cache, 1:1. And then there is the set associative. Just as its name says, it uses sets. So let me explain fully associative first, and then I'll use the fully associative and the direct mapping to explain set associative. In fully associative, what we do is all of the RAM spaces are available to be used. And I said it will be explained better in the next lesson. So all the cache spaces are available to be used. So every data can just move from memory into any empty available cache as directed by the CPU. That one is too many. Each data can go everywhere. In the second one, though, that is the set associative, it is moderate. It combines properties of the direct mapping with the fully associative in the sense that it maps particular data to particular sets. Each set is a group of a number of cache spaces. So this is what the lecturer was trying to explain in the previous lesson. So each set is containing a particular number of cache spaces. So what this means is we are employing the direct mapping in the sense that we are still assigning particular spaces to particular memory addresses. However, when we come to this side, the data that will be held here can either be held in this side or this side. So there are still options to pick from. This brings moderacy. So then it's moderate. Since we are not strictly using this, in case this is taken, then we can also come to this side. So then the set associative is the one that is used in a lot of modern computer systems, since it's very efficient to use. Let's keep that in mind. So memory cache, the direct mapping when we are moving from memory to cache is 1:1. Each memory space is assigned a strict cache location, whereas associative assigns breaks the cache into groups and then assigns memory spaces to particular groups. And within that group, it can sit or it can take any of the spaces provided it is empty, or it might replace another data if all spaces are still empty. Then we have the fully associative where each one is assigned to every memory block is assigned to every cache block. So it can go into the cache and then go and then sit at any random place. Is this clear? People, is this clear? Right. Right. We proceed. Okay, we proceed. So now there is the Accra traffic analogy, and then we are going to use that to try explaining all these different types of data movements or data transfer types. Okay, so now it says memory bus. Think of the memory bus as the Achimota highway. So the bus is basically a pathway through which data moves. And then there is cache. Cache is the VIP express lane. It's limited. It means only a few people have access to it. But due to that reason, it is fast. Because if only a few people are moving on it, a lot of movements can happen on there. And then there is the main memory, which is the busy side streets, that will be a NAMSO. And then data is the vehicles that are being moved along these lanes. Now it says if the VIP lane is full, a replacement policy diverts cars for emergency vehicles. So this means that if the VIP side is full and someone like the president is coming, we can easily find someone on the road in the VIP that is not held in a position that is viewed as the level of presidency. And then we quickly take that person out so that the president can do what? Take his place on the lane. However, if the president is coming and there is another president on the road, this will mean that that president and then the new president will now have to either isolate every other person or try to move every other person, or the two of them will battle for the position on the road. What we do here is, and what most architecture use is the least recently used. That's the LRU here. And it's a replacement policy that basically removes data that has been held in memory so long and hasn't been used for a while. The memory sees that its priority is low. Since it's not going to be used anytime soon, it can move away. And then when we need it at a very later time, we can go into memory and retrieve it. So cache will take away these data and discard them, making room for more important values to come in. I hope that makes it clear. So that's the least recently used policy. It removes the card that is parked the longest. So now let's answer this question. It says in a cache using the least recently used, which block is selected for eviction when a new block must be loaded? In a cache using the least recently used policy, which block is selected for eviction when a new block must be loaded? Is it 1, the block that has been in the cache the longest time? 2, the block that hasn't been accessed for the longest time? 3, a random block chosen by the controller? Or 4, the block that was accessed most frequently? Very tricky answers. Let's consider them carefully before we answer. Yes, are there any answers? Or I should point a few people out? Okay, I spy Richard. But Richard, would you like to share your answer on that with us if you are active? In the least recently used policy, which block is selected for eviction? Can I be heard, people? Joshua, can you hear me?
Yeah, I can hear you, sir.
All right, all right. So I've been boosted. Okay. What about you, Mr. Ebenezer? Mr. Ebenezer, which one do you think will be evicted when we are using the least recently used policy?
I think C.
C. C.
C.
So C says a random block.
Which is 3?
B.
You said B. B says the block that hasn't been accessed for the longest time. Someone says C, the random block chosen by the controller. Okay, let's see what the right answer is and why it is the right answer. So the correct answer is the block that hasn't been accessed by the longest for the longest time, and that goes to whoever said B. The lady is Monica. Oh, okay, I see. Powerful. Why is this? Least recently used literally goes to the least recently used, like the one that hasn't been used in a long time. How does this differ from the one at the top? It says the block that hasn't been in the cache the longest time. That has been in the cache the longest time. That's different from the one that has not been used for long. You may have been in the memory for the longest time, in cache the longest time, but it doesn't necessarily mean that you have not been accessed. So it means you are still on the priority list. But the one that has been there and has not been used, out of all, the longest time is the one that will be taken out in the least recently used policy. So it's evicted first. All right. Cache-aware programming. Software engineering involves understanding how hardware handles data. Writing cache-aware code maximizes locality, spatial locality. Accessing memory sequentially allows the central processing units to fetch blocks of neighboring data efficiently. Random access wastes time fetching new blocks repeatedly. This leads to faster execution without hardware upgrades. So if you are a software engineer and then you are constructing a particular program, perhaps you should take into account which data is more likely to be accessed if one particular data is also accessed. For example, if a user is, if there is someone that is signing into a site, bear with me, and every single time when they come, they enter their name, their ID, their email, and they enter about 5 different details. You can make it so that there will be a save button where they can save their details. And whenever the person enters their name, memory will now load, or the CPU will now load immediately data like his ID and etc. that will be needed for he to log in to the site, for him to log into the site. This means that you have maximized the use of spatial locality, because you have now brought more most likely to be accessed data to a place where the CPU will now use them to the user's advantage. So then there is actually hardware handling, or hardware handling of spatial locality, and then there is the software aspect of it. And then the software aspect of it mostly comes with the user and then the programmer, that's the person creating the codes. So if you are a programmer, you take into account what will be needed when one thing is taken. That way, when a user is using your interface, it makes it seem like this is a very convenient thing. It's like the design is very human. It understands the pains of a human, how it's tough to enter your ID every single time you log in, and etc. All right, keep that in mind. So then, software engineering involves understanding how hardware handles data. Writing cache-aware code maximizes spatial locality. Mr. Joshua Calvin, am I the one who is to check my network, or does it refer to a different person?
I'm referring to Calvin.
Come again? Oh, okay, all right.
I'm referring. Yeah.
To Calvin, yes. Let's proceed. So then, traversal, how data is accessed in arrays. So then there is a row major traversal where it is done by rows. And then there is the column major traversal where it is done by columns. In a physical memory space, data may be accessed by contiguous access. And then there is strided or jumping access. Are you familiar with any of these terms? And if you do, can you explain what they mean to us? Yes. Is there anyone who is familiar with these concepts and would like to elaborate on it? Right. Then if no one is willing to talk, then I assume you do not know. So then we can just go right to it. Let's start with the row major traversal. If you are coding in a program, let's say you are using C++, a row major traversal makes it possible so that data is accessed just as its name suggests, row after row. So then when data has been stored in a particular matrix format or whatever, it will be accessed from one row to another, making it so that their arrangements will now pile up into a meaningful interpretation. Let me see. I want to write on my screen. So So let's see how this row major traversal works. Okay, assume you have created data and then it is held in a matrix such as 1, 2, 3, 4, 5, and 6, like this. Now, if we are using row major traversal, when the data is being read, it will be read row by row. So it reads this row first and lists it as 1, 2, 3. Then it reads this next row and then it reads it as 4, 5, 6. In this way, if you have coded yours using row major traversal and then your codes are written in an order where it can be read row wise and then the structure will be maintained. This is exactly how it will be read by your program, and then it's called row major traversal. Column major, on the other hand, does the vice versa, where it will access columns first, like this, and like this, which might give you a different order, unless, of course, you programmed it in with respect to how the column major accepts data. So if you want to maintain order, maybe you may have decided to do it as 1, 2, 3, 4, 5, 6. And that's why it says you should be cache aware in your programming. So then it accesses this way, and then this way. That's column by column. So that's column major traversal. And then in the end, it will give you the very same values, such as this one. This is just a demonstration. That's not like exactly it, but this is a very close to the idea that we are trying to establish here. Okay. Why does this matter? If you know how these things work, you'll be able to use them to make inferences when you're constructing your code. Knowing which order will be very good for my arrangements, okay, depending on the type of traversal you have chosen for your accessing when it comes to your cache design. All right. Now, there is also the continuous access, and then there is the sharded access. These ones are simple and they will need no demonstration. Continuous access basically says that you access data in a fixed sequence. So as you can see, we check this before we check that, and we check this before we check that. We keep checking the data values in a particular order so that we do not miss any spots. However, sharded or jumping is not advisable. Reason being that when it is being done, currently, you jump from here to this side, jump from here to this side. Just like what we demonstrated earlier in the column major, what do you see? If the data from this side is read through columns, what we are going to have listed will be 1, 4, followed by 2, 5, followed by 3, 6. This means we read memory addresses in indefinite orders, making it sometimes possible to overlook particular lines that require or that needed to be read first, or that needed to be referenced or addressed first. So then the column major sometimes can lead to problems like this, since it might mess up the order in which the code must be read. And then there is that is what it goes further to say that you use a sharded or jumping access, where you are jumping from column to column. Okay. So then it says in this one, you are jumping from column to column. So we stand here, we jump to this side, and we jump to this side. Then in that case, we are missing spots in memory and they never get read. So it's not ideal for programming, is it? Right. So now it says traversing a 2D array column. Yes, Mr. Emmanuel. Mr. Emmanuel.
Yes, Mr. Prince.
Yeah.
You presented to us a question.
Yes, please go ahead.
So please, can you go back to the previous slide?
The previous slide or the page where I was writing. This one.
No, like the previous slide. Yeah, this one. So
Yeah,
for
this.
retrieving data between the row major traversal and the column major traversal, which one is faster? Retrieving
So
data.
some programming devices or some programming software or systems actually make use of the column major, but then the row major is ideally sought out is ideally sought out due to the fact that it is easier to use and it requires not too much understanding. Column major, in order to execute, must be done with extreme care, else you risk messing up your program structure. Okay, so row major is the one that you are advised to use, but then you are not being stopped from using column major. It's used in fourth round programming languages, like programming languages that are typically done by like people who have very big or very much, I don't know, very high expertise. Good. That's the right way to use the words. Good. So then you can use either, but row major is best sorted for simpler programming. Column major is used for things like Fortran or MATLAB. But then remember, in the contiguous access, it is fast. It is fast. Strided access is also supposed to be fast, but then it is slower. Reason being that you are skipping through memory with a gap. This means you risk overlooking particular data values and you might have to come back to them later to identify where they are, especially if it is not written with care. Okay. So then row major is row wise, column major is column wise. That's all there is to it. Let's answer this question now. It says traversing a 2D array column by column in a C language program, which is row major, is generally slower than row by row traversal, true or false. So if a C language program, which follows the row major architecture, and you are using a column approach, column by column 2D approach, which one do you think will be best for accessing data? And then, do you think it's slower or it is faster? That's the question. Now we use column major where row major is supposed to be used in a C language program. Is it generally slower than the row by row? Yes, Mr. Joshua.
No, for me, I'll choose false.
It's false, right? So then the column major is generally faster than the row by row. Okay. What about the rest of us? Do we agree to his false answer, or you have different opinions? There is a why aside to it. Oh. Mr. Joshua, why do you think it's false though?
Because the column to column traversal, I think it processes data. I don't know how to say it.
It accesses data faster. Like it accesses data faster, right?
Yes,
Oh,
that's it.
okay, okay. All right. So now there is something we call stride, right? Stride talks about how long you jump. In row major, you can straightly jump one step. However, in column major, you can jump greater than one step. The advantage of row major is you will check every single box. So then you won't even have to come back to check. But in column major, you risk overlooking some boxes because you are jumping more than one box at a time. And then you might have to come back. Let's see which one makes it slower when we are doing row major strictly and then we decide to go with column major. Okay. So then it says, why is that? So traversing a column road, it is true. It's generally slower. And why is that? Because column major access causes frequent cache misses due to poor spatial locality. So it causes frequent cache misses due to poor spatial locality. This means when it is carrying data, it might overlook some data from certain regions that are related to the data that you need. This will mean that all those data will be left behind. And now when you want to access them in cache, it will now have to go and then read memory again and retrieve this data to you, making it slower. So then there's a chance of you missing a lot of the data that you'll be trying to hit on your cache space. That's why it is not advisable. And they said because the compiler cannot optimize column by column loops. Okay, so it cannot optimize. Can optimize means it cannot make a good use of them for efficiency, basically. Therefore, you are not advised to use column major in a language program that strictly goes with row by row. So remember, languages like C, they use row by row. Okay. However, higher ones, yeah, they use other things like column major. Okay. So is that clear? All right. Let's proceed. So now it says the conceptual map for memory hierarchy. We already know how this works, but this 3D model shows it quite clearly. And then I think it's good that we look at it. So it says memory hierarchy registers RAM, cache. Registers in level 1 cache are the fastest, smallest, and they hold current working set. So they are always holding data that is currently being used, like every single time. While level 2 and level 3, they bridge to the RAM. So they serve as a pathway to the RAM. And then they store recently used data and they use inclusive policies. Inclusive policies meaning that they hold data for level 1 as level 2, and level 2's data is held as level 3 as well. The main memory is RAM and it is slower and it holds less frequently used data. Optimization goal will maximize data in faster upper levels. So it will maximize data movements or data availability in upper levels. Remember that the level 1 cache and registers are the highest level there are. Level 2 and level 3 are slightly higher than memory and main memory. Okay, so level 2 is higher than level 3. Level 3 is higher than main memory in that order. All right, so here is what it looks like. At the top of this pyramid, we have our CPU. And then what is closest to CPU is our cache. And then beneath the cache, we have level 2 cache. So level 1 cache is a level 2 cache. As you can see, level 2 cache is larger than level 1. This means it trades off what? Speed, right? It trades off speed for size. And then we have level 3 cache underneath that. Okay, so then we have several different caches. Looks like this is level 1, this is level 2. This one here is a build of level 3. It's an AI image, so it's a little messed up, but you can get the idea. You can see from the right sense here, it's messed up. And this one is the random access memory. That's RAM itself, having the most amount of space, however, the least amount of speed. Now, let's answer these questions quickly. What does LRU stand for in eviction policies? What does LRU stand for? This one, we expect the answer within a minute. Otherwise, I'll call somebody and torture their lives. I'm telling you. So what does LRU stand for in eviction policies? Okay, let me call somebody. Right, so who is here I can call? Mr. Emmanuel Boabeng. Please, if you have followed with us from the start, what is the LRU? What does it stand for in eviction policies? Okay, I think Mr. Emmanuel Boabeng is tired, so it's not like he doesn't know, he's just tired. That's why. Yes, Mr. Joshua Annan, what does LRU stand for in eviction policies?
Least recently used.
Least recently used. Thank you very much. That's a correct answer. Which mapping technique allows a block to reside in any cache line, in anyone at all? Which mapping technique? Is it direct? Is it set associative or is fully associative? From what we have discussed.
Fully.
Which, yes?
So it's fully associated.
The fully associative, very good. So fully associative allows a block to reside in any cache line. Does row major traversal exploit temporal or spatial locality? Does row major traversal exploit temporal or spatial locality?
It's all locality.
Temporal.
I mean, okay. I've gotten
Spatial
two people saying temporal.
locality.
Okay.
No, it's
And is
spatial.
which one are you choosing? Temporal or spatial?
Spatial. I choose
Okay.
spatial.
All right. So primarily, row major is actually about spatial locality, taking data that is likely to be accessed when one data value has been read. Okay, so if I take something like I know that whenever we take a cup, we are likely to use a spoon. Then if I am sent to go to the kitchen to pick a cup, because I am lazy, I'll not come back and let them say, go and pick a spoon. So I pick my cup, I pick my spoon, and I even pick my saucer. Matter of fact, I'll even bring a sugar along just because I don't want to go back to that place. So then it's convenient for me. It makes it faster for whoever I am giving it to. So then bring the cup, Nana, then pat, it's already there. Nana, bring the sugar, pat, it's already there. Bring the spoon. That is what spatial locality is about, okay? For the temporal locality, it will mean that we are storing everything together. That's we might need. So we store Gary sugar and everything at one place. Doesn't necessarily mean that we carry them together though. Row major primarily, and it also uses temporal, but primarily it works on spatial locality. All right, so we have done well. We have done well. A summary. The traffic management, replacement policies like least recently used, manage data flow. And then there is the prioritizing, important information like traffic officers, okay? There is software impact, cache-aware programming by optimizing array traversal, boosts software speed through spatial locality. So if you understand how the programming language you are using works, so let me just mention some programming languages and the type of locality they use. And then when you are when you become when you reach a level of programming where you can casually use arrays, right? You will know which type of array addressing or array value addressing you should be using in order to maximize the speed of your software. So then, let's see. Some programming languages like C, C++, I think we've already mentioned programming C, C++, Java, Python, the common ones that we know. Rule of thumb, they use what do we call it, row major traversal, whereas higher ones like Fortran programming languages or MATLAB or Julia programming, these ones that are not used frequently by most people due to the fact that they require a step higher up the ladder, are the ones that are also more known to be using column major traversal. Then we have the design trade-offs. The memory hierarchy balances speed, cost, and capacity. So the more speed you have, the higher your price, and then the smaller your storage. The less speed you have, the less your price, and then the higher your storage capacity. So you either have one, but not the other. So let's see. Here are some mixed objective questions. Let's try answering them. These ones are not even objective. What is wrong with this software? So define spatial locality. In your own words, what would you say spatial locality is? Someone should use a well-phrased English, use well-phrased English sentences to define the spatial locality. Feel free to try, okay? We are on slide 17 of 18. We still have some time to spare, so we will move on to the next slide and we'll hammer this concept even better so that it gets plastered in our brains basically for eternity. So is anyone willing to, let's see, okay, hey, five people active. Sorry, our hands up. I'm sorry. Oh, Mr. Joshua. Yes, let me hear you speak.
Please, did you say spatial locality?
Yes, it says define spatial locality.
So the ability of a program to reference units of memory whose addresses are near one another.
Excellent. Ability of a program to reference units of memory whose memory addresses are near or are close to one another. That defines spatial locality very well. What is the main disadvantage of the fully associative cache? I never really spoke about the advantages and disadvantages because I said we'll cover that properly in the next slide. However, what is the disadvantage? What do you think the disadvantage of a memory what do we call it, mapping strategy that allows you to access any random space at any time from when you're coming from memory to cache? What do you think the disadvantage is? What could go wrong? We don't know what could go wrong, right? Okay, so here's what the problem with that is. since the memory data coming through from memory to the cache will not be the only one that is probably being held at that time or currently being used. This will mean that the CPU or the program's control will now have to read the entire cache simultaneously, read every single thing at once, and then trying to identify which space is open before it moves particular or it removes the particular memory data to that side. So then the disadvantage is this will make it slow because it has to read all these ones. So it makes it relatively slower than direct. Okay. It's directly slow and relatively slower than direct. Explain the difference between inclusive and exclusive cache hierarchies. Oh no, sorry, there's another. It says true or false. A write buffer reduces central processing units stalls during write operations. Is that true? If the central processing unit always has to fetch data from RAM, well, that affects its speed. If a write buffer is brought into the equation to be holding data temporarily as we are writing data, will it reduce how long the CPU takes to do processing or not? True or false? Musana Motie, Dr. Matilda tried the Akamosumo engagement. We are engaging you to you don't want to talk. Okay. Yes, Mr. Emmanuel.
Yes, yes, I would choose true.
Yeah, it's true. Exactly. It is true. It is true. Now, he's right. Okay. Next one. Explain the difference between inclusive and exclusive cache hierarchies. The hierarchies. Yeah, I think the word should be hierarchies, not hierarchies. Hierarchies. Mr. Emmanuel, your hand is still up. You want to go again? Please tackling this one for us. How does inclusive and exclusive differ? Hey, Mr. Nyako, and then who show crowd? Like serious, bro. Are you okay? Are you fine? Yeah, Mr. Joshua, let's go.
So the inclusive cache, the level 1 cache, it's a subset of the level 2 and level 3.
Level 1 is a subset, meaning level 1's data is held in level 2 and
Yes,
3.
it's held in level 2, level 3.
That's a
But
very good way to put it.
the exclusive is it has no duplicate.
So each one's data is irrespective of the other.
Yes.
Powerful, powerful. This Charlie, hey, I mean, it's all been so I'll be a guy. Okay, okay. Allah, good more. That's nice. Let's move on to the next one. So in the formula of average memory access time is equal to hit time plus miss rate times miss penalty. What happens if the miss rate doubles? Does this increase average memory access time or it reduces average memory access time? Ali, we are recapping what we've learned. So share an answer so that it will be wrong and we'll correct you and you're going to write it in your exam. Let me call some of the big men. Mr. Abuaje Prince, today I'm not seeing your show, bruh.
They think they are sure say where's the World Champions League?
Come again?
I sure say where's the World Champions League?
I see.
So
okay.
I think the amount will increase.
The amount will increase. So the average memory access time will increase if the miss rate doubles. Do we agree with what he is saying? Mr. Ebenezer Nyakon, what about you?
Yeah, I do agree with him. The amount will increase.
That's very good, very good. So good thinking, Mr. Eben and then Mr. Prince. And then that's actually correct because since we are finding the products, this will mean that an increase in the miss penalty will be directly proportional to the average memory access time. Basically, if the miss penalty increases, the memory access time for the memory space that we are referencing now also goes high. So it means it will take us more time to get the data than we were taking at first. This, in the long run, increases the average memory access time in total. Why is direct mapped cache faster to search than set-associative? Yes, Mr. Ebenezer.
I'm trying, So I think
Yeah.
it takes only one direction.
So since it goes to only one direction, we don't need to search much, right?
Yes, please. There's no searching.
Exactly. That's the exact reason. So since it has a predestined place, so maybe I'll call that. So when the data moves now straight to that side, it's faster to use, despite the fact that you might have to be kicking out data every now and then. That is the trade-off, by the way, but it's faster to use. Okay. Now, next one says, what does a cache line or block contain? This one I've not mentioned, but I'll mention it better in the next lesson. But if you know it, feel free to share. Cache line or a block. So since I've not mentioned it, let me just go ahead and talk about it. So what it basically contains is a chunk of data that has been copied from what's main memory. So if like, okay, Mr. Ebenezer, go ahead.
Okay, so I think a cache line contains valid bits. Then the other one is data line.
So data line, valid bits, right? So then the
And these are
appropriate
the two I
terms
can
is,
recall.
oh, that's great. That's great. So then the actual terms that he's trying to help us with are the data itself. That's the main thing. And it has a tag, it has a valid bit, and then sometimes there is a dirty bit. And then there's also a replacement information for it. Okay. So then the line itself contains the data. The data is the main thing. So the block of bytes that are carried into the cache, that becomes the data. And then the tag identifies which block exactly this data. Data we create here. Where exactly is it coming from? The tag is like an address that points to that side. And then the contains valid data. So sorry for that network break. So what cache line contains valid. What is that?
Please come in.
Sorry, please, can you hear me? Someone keeps calling me. Someone keeps calling me. Sorry. All right, let me proceed.
Yeah.
Good. So I was saying that the valid bits, okay, it tells us whether the cache line contains valid data. So whether the data is holding is empty, that will mean it's invalid, or whether it is usable, then it is valid. So maybe a 0 or a 1. So it deals strictly with bits, so zeros and ones. Okay, someone keeps calling me, so the network keeps breaking. Or first view, my I've hung up and then you still call. Let's move on to the next one. There is the optional, that's the dirty bit. So if there is a valid bit, then there's an invalid one, right? So for write back caching, this one tells us whether the data was modified when it came to the cache memory. If it's dirty, it must be written back to memory. Like if it is not, what do we call it? Changed. If it comes in a state that it is valid, but it is still not exactly preferable, then it must be sent back or written back to memory. Perhaps it will be written, altered a little, and then it will be stored back in memory. And then also there are replacement info. These ones are used for things like the least recently used, what we call it, eviction policies that we mentioned earlier. It helps us to tell which line to evict and which one to keep. Okay. So then in general, it contains a chunk of data that has been copied from memory. But this data contains the data, that's the main thing, the tag, which tells us where the data is, whether it's the valid bit, the invalid bit, the optional or dirty bits, and also the replacement info. Okay, so you can choose to exclude the dirty bits and the replacement info and stick to the valid bits, the tag, as well as the data. Okay. All right. Let's continue. Last one. How does temporal locality differ from spatial locality? Okay, this one is easy. one is easy. I think there are some questions, but they have been squished down. So to summarize the lesson, let me just give you that one and we end. So in temporal locality, data that are likely to be accessed or data that are mostly accessed with each other are stored together in one region. However, in spatial locality, data that is likely to be accessed is carried or is moved together with all of, so current data being accessed is moved together with data that is likely to be accessed to. That's for spatial locality. So if I go into a room, I mentioned earlier that I have been sent to the kitchen to go and pick a spoon. And I know that whenever they ask me to go for spoon, they often tell me to go and bring a cup, bring sugar, bring gari, bring Milo, bring fanchoko, whatever. I decide to pick all these things together so that I bring them and immediately I put them on the table. And immediately they say, give me sugar, I just pass it. Give me milk, I just pass it. That is the application of spatial locality. Whereas in temporal locality, the milk, sugar, and everything in the kitchen will be stored at one place so that if you need it, you can easily go and then retrieve it. Okay? Remember what a cache line contains. It contains data, it contains your valid bits, and then it also contains what? So data, valid bits, and then the tag. The tag which tells us where exactly we are getting data from. Right. So then this is a question here. It says design a cache hierarchy with level 1, 2, 3 sizes for a database server with frequent reads and fixed budget, blah, blah, blah. And there is another question. With this one, it says justify your choices. So what you are going to choose concerning the requirements of this, justify your choices, decide between an inclusive or an exclusive hierarchy, explaining the impacts on total storage. So these ones are just self-assessments and you can go and do them in your own time. And perhaps next time in our next lesson, share with us what your ideas were. Or maybe better still, put those ideas on our platforms, okay? It's, it's good for engagement. And then we also have a 1,000 by 1,000 image matrix program is slow. Identify the likely cause, cache misses, and then optimize traversal loops for spatial locality using pseudocode. For this one, I'll say perhaps for some of us, it is beyond us, right? It's understandable, but then it is not the main objective of this one. We have a few minutes time. Let me walk you through what the next lesson is about. As a matter of fact, I think that will be enough time to cover all of the next lesson. However, I wanted us to really do 5. We have discussed a lot of the things in chapter 5, by the way. The addressing strategies, the eviction policies, and etc., the mapping strategies too. Let me see. Right. So introduction to cache memory, even further. So this one builds on what we have already learned since the fast crana MP being 18 actually. It was 16 slides. Let's go. So by the end of the lesson, you should be able to explain the speed gap between the CPU and the main memory. So I prepared this slide so that they will be able to explain the things in even deeper detail. I know it really helps when we use analogies to explain. So in even deeper details using analogies. So you should be able to define cache memory and its purpose, understand the locality of reference. So whether we are dealing with temporal or spatial locality, describe the basic operation of hits and misses, and evaluate the cost versus performance trade-off. Okay, let's get right into it. So now look at this one, the memory speed gap. And this is an analogy to make you understand it very well. Imagine a super fast head chef, and that head chef is the central processing unit. The head chef can chop vegetables in a single second, like very fast. I'm talking prap, and he's done, prap, and he's done, very fast. However, their assistants, which is the RAM, it takes 100 seconds just to bring the vegetables from the storeroom. What is this implying? The chef spends most of the time waiting instead of cooking. He can cook. The computer feels slow. This means the central processing unit has the ability to process data very fast. But the person, that's the assistant, that is supposed to bring the data to be processed, takes a lot of time to bring that data. So the speed of the central processing unit becomes redundant. It becomes useless. For the reason that even if I am fast, at the end, in the end, I'll cut it fast, but still, all the access time that was used to bring it here has already been wasted. Does this make the concepts even clearer to you? Because I know it would have made it clearer to me if I was a student in this scenario. Right. So keep that in mind. A solution we can do is we can place a small basket, that's a cash, right next to the shelf. And inside that basket, we will now put things that the chef can easily access instead of now depending solely on his assistants. So then the location, is physically located between the central processing unit and then the RAM. So the basket will now be a connection between who? Your chef and then your pantry, or in this case, who is the person? Your assistant, right? So then it serves as an intermediary. And its function is that it stores the most frequently used ingredients. That's data. So if the chef and the assistant realizes that, oh, the chef is preparing ebunu ebunu, then he brings things like kontomri and then kantose, and he puts them in the basket so that he knows the chef is going to definitely need these things. So he prioritizes them and puts them right there so that the chef can easily access them. So the most frequently used ones are stored closer to the chef. The speed, the types of RAM we have the static RAM, and it provides very fast access due to the fact that it uses quite a lot of transistors. Could use about 6 transistors for moving a single bit of data, almost like a waste, right? But then that's a lot of speed guaranteed. But it is much smaller due to the fact that it is very expensive to make. Now the chef grabs what they need instantly from the basket. So then here is a representation. The CPU and then the RAM is very slow. The cache takes data from this side. The cache uses static RAM. So you see the cache is a type of RAM and it uses static RAM. And it takes the data from the dynamic RAM and it holds it. And then the CPU will be able to get data very fast because the cache has very little access time. And then it is sent back to the CPU, which is the chef. We are just explaining and hammering on concept that we've already discussed. Then the locality of reference. This is the principle by which we do data referencing a story, by the way. Why does the cache trick work? Because computer programs behave predictably. The temporal locality works with time. The analogy is that if you read a book today, you will likely read it again tomorrow. So if data is used now, it will be used soon. So in temporal locality, the CPU demonstrates an ability to find data that is likely to be used because it was just recently used. Then we have spatial locality. The idea is if you pull a book from the shelf, you might also need the one next to it. And I've already used my kitchen and Gary and spoon analogy to explain this. So if data is accessed, nearby data will likely be needed next. So they are all fetched together. How cache works. Step 1, the request. The central processing unit asks for specific data and it checks the tiny fast cache first. The tiny fast cache will be the level 1 cache, which is the closest to the central processing unit. When it checks the cache, there is an outcome, that's step 2. It might either hit or miss. Hitting is a term used to describe data that we find in the cache. So when data is found in the cache, due to how fast the cache is, that data is quickly moved to the CPU and processing is almost instant. However, if that data is not found on the cache due to the limited size of the cache, then we consider that a miss. This means that we will have to go outside the cache and fetch the data from the RAM, which we know has a slower access time. So hitting is what happens, or a hit is what happens when data is found on the memory that is being searched on for. So in this case, the cache. Whereas missing is when data is not found on that memory and it has to be brought out from an external memory source. In other words, a lower level memory. Step 3, the transfer. On a miss, a block of data containing the needed item now moves from the RAM to the cache. So there is the request, there is the outcome, and then there is the transfer. If there is a miss, data is transferred from the RAM all the way to the cache, then all the way to the CPU. So it shows you here RAM, then the block is carried all the way to the cache. Then the cache now sends it to the CPU. Now, visualizing the read process. So let's use a flow chart to visualize what is happening. The central processing sends a request to the cache. If the cache has it, it immediately delivers it to the central processing unit. However, if the cache doesn't have it, it comes, so whenever you send the data, it does the second condition, it checks. Did we find the data we needed? If yes, then straight ahead, it comes back to the CPU and then it gives the data to that. That will be a hit. However, if the condition was a miss, then we will now visit the RAM, retrieve data, carry it back to the cache. And the cache is very fast since it's using static RAM, and then it forwards that data back to the CPU. So this flowchart shows you the read process even better. Now, tell me what happens here. What will happen to a computer's performance if cache memory did not exist at all? What will happen to a computer's performance if cache? This is a simple one, so someone should just take it for us and we go. They're not going until someone becomes a Jesus.
I think
You may unmute and
computer will
speak.
be slow.
To be extremely slow. Thank you. Well, also, thank you. Okay. So then, will be extremely slow. He's right. So he says the CPU will have to wait for the RAM for every single piece of data. System will run significantly slower because the fast CPU will be constantly bottlenecked by the slower RAM speed. Tasks like gaming or video editing will be nearly impossible due to the lag. Right. Cost versus performance trade-off. Static RAM. It is used in cache memory. It is very fast and it matches the speed of CPU. That's crazy fast. It is very expensive. And then it uses 6 transistors, 6 whole transistors per a single bit. And the density, it stores less data per physical area. So it means in order for it to do what it is capable of doing, it has to lose its size, and then it also has to use very high-end materials, making it very expensive. And it matches the speed of the CPU, and it is used in cache memory. Then we have the dynamic RAM. It is used in main memory, which is RAM. It is slower than the central processing unit. It uses only one transistor and one capacitor, sorry, per bit, and it stores huge amounts of data. Huge amounts of data. So what does a cache hit mean? Oh yeah, now people, let's kill this one. It's a simple one. Data was not found in cache. Data was found in cache. CPU is damaged. RAM is full. What does a hit mean?
That was found in cache.
RAM was found in cache. Excellent. So then the data, sorry, not RAM. Data was found in cache. Good. Which principle state that if a data location is referenced, it is likely to be referenced again? If a data location is gone to,
Temporal
it is
quality.
likely temporal locality. Thank you. Deals with time. Why is cache memory usually very small compared to main memory? Yes, they also have a why is cache memory usually very small compared to main memory? It's very expensive, it's too slow. CPU cannot address more space. It uses DRAM technology.
I think it is the RAM technology.
Okay, he says it uses
It's expensive
DRAM
to build.
technology. It is expensive to build. Okay, are there any more ideas? But then the correct answer is the expense. Cache uses static RAM, and static RAM uses 6 transistors per piece, and it's very expensive to make. So because it is very expensive to build, that is why it's usually very small. And then DRAM is strictly used in main memory, okay? So that is not the right way to go. We have come to the end of today's session. If you have any good questions, please feel free to go ahead and ask now, or else remain silent. Hold your peace. If you have any good questions, please feel free now before we bring this session to a close. All right. So thank you for being wonderful listeners tonight, wonderful learners. Have a great night. Have a great sleep and have Yo, Joshua, for some reason I'm unable to end the meeting so can you do it? I keep clicking end meeting, but it's not ending. Or Mona, if you still have administrative rights, please do
Okay,
that for me,
sure.
okay? Yeah.
Or